In this lecture, we shall consider some more advanced level problems on motion in 1 and 2 dimensions. Kinematics is an important chapter of mechanics and a favorite with examiners. As usual, we shall classify the problems further in grades 1, 2 and 3 depending on their difficulty level. So here is the first problem in the lecture, which I put at difficulty level 3. And this one is telling that a plane flies in a straight line from point A to point B and back. In calm weather, that is in absence of any wind, the plane makes the round trip in time t at a constant speed v. What time would it take to make the trip if a wind of speed w blows in part A at an angle theta, in part B perpendicular, and in part C parallel to the line AB? Check whether in any of these cases the presence of wind reduces the time of flight. If you refer to my theoretical lecture on motion of a boat in a river, you'll be able to understand the problem better. So let's understand the situation here first with a simple figure. This is the line AB along which the plane needs to fly. A is the starting point of the plane, AB is the line of motion, and B is the end point of the forward trip, and the plane travels from A to B in the forward trip and then again back from B to A in the return trip. So the round trip becomes A to B and then back to A. They have said here that if there is no wind, that is in calm weather, the plane makes the round trip in time capital T. So let's assume the length AB, that is equal to L. So the time of flight for the round trip, capital T, is the time taken for the forward trip from A to B plus the time taken for the return trip, that is from B to A. Now in the forward trip, time taken is the length AB, that is taken to be L here, divided by the constant speed of the plane, that is taken to be V, and similarly in the return trip also the same length with the same constant speed, and therefore the time of flight for the round trip is coming out to be twice L by V in the absence of any wind. I'll be making use of this in future, so I'm calling it equation number 1 for future reference. Now with this understanding, let us now go to the first part of the problem and see if a wind is blowing at an angle theta with the direction of AB. Now when the wind is blowing, as I show by this blue arrow, with a velocity w at an angle theta with direction of AB, the pilot will direct the plane in such a direction that I also show by this blue arrow, and this is the velocity vector of the plane now. This V is no longer along the line AB, but an angle, say alpha, with the direction of AB, so that the components of W and V perpendicular to the line AB, they cancel each other out, so that there is no net component of the resultant velocity of the plane perpendicular to the line AB. Let me show it also graphically here in my figure. Suppose W is resolved into its two components, and this component perpendicular to AB is W sine theta, and similarly V is also resolved into its two components. One is along AB and the other is perpendicular to AB, and the one perpendicular to AB, if this angle is alpha, it is of course coming out to be V into sine alpha. I said the pilot's intention is to direct the plane in such a way so that W sine theta cancels out V sine alpha and there is no net component of velocity perpendicular to AB. Let's also write down in the figure the other components. The wind has a component of W cos theta along AB, and the plane itself has got a velocity component of V into cos alpha along AB. So with this understanding, we write down, considering the components of velocities perpendicular to AB, if these two components have to cancel each other out numerically in magnitude, V sine alpha must be equal to W sine theta. And it follows therefore that sine alpha, alpha being the angle at which the plane is directed, sine alpha can be written to be W into sine theta divided by V. Let me call it equation number 2 for future use. Let us now see the components of these two velocities in the direction of AB which are responsible for the plane's flight along the line AB. I am calling this velocity as velocity resultant, R for resultant, along the path AB, VRAB, that is given by V cos alpha, the component of plane's velocity, plus W cos theta, the component of wind velocity along the line AB. Once we have got the value of sine alpha earlier from equation number 2, let's improve on it. I could write this thing to be V into square root of 1 minus sine square alpha, isn't it? Cos alpha is given by this formula, plus W into cos theta. In my next step, I put the value of sine alpha from equation number 2, and that is giving me V into square root of 1 minus W sine theta by V. This is whole square plus W cos theta. In the next step, as you can show yourself, if I took V square in denominator inside the square root, you show it eventually, I could write this thing to be square root of V square minus W square sine square theta, and you have also got plus W cos theta. Now, since we have got the resultant velocity of the plane along the line AB during the forward trip, by the expression we can find out the time taken for the forward trip, that is TAB in the presence of wind, that is given by the length of AB, that is L, divided by resultant velocity along the line AB. This is giving me L divided by square root of V square minus W square sine square theta, whole thing under square root, plus W into cos theta. So that is the time taken for the forward trip from A to B. And let us now find out the time taken by the plane in the return trip from B to A. And therefore, I introduce one more figure here. If it helps you, let me call this as equation number 3. I'll need it in some time. And for the return trip from B to A, well, the wind direction remains unchanged as before. So I'm showing it here, the same wind velocity W at an angle of theta with AB. This component is W cos theta, and this component perpendicular to AB is W sin theta. Now this time, the pilot is directing his plane at an angle of alpha with the direction BA, isn't it? Because he has to return now from B to A along this straight line only. And once again, if this V is the plane velocity.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.